Hello, everyone, and welcome back to the last part of our session today. So we have our last preliminary talk today, followed by a panel discussion to wrap up all the discussions we have had. So it is my pleasure to introduce our final speaker of today, Professor Jonathan Hurst from Oregon State University, who's going to talk about human-centric robots. So thank you very much for joining, Jonathan. We really appreciate it. And I'll hand over to you for your talk. Thank you.
Excellent. Hi, everybody. Can you hear me okay? I think I'm all set up properly.
Perfect. We can hear you, see the screen. Amazing. Thank you.
Okay, so thank you for that. I'm Jonathan Hurst. I'm going to talk about human-centric robotics and really creating an embodied artificial intelligence. These are words that have existed for a long time, but are starting to become more and more relevant as they're used in the news and more broadly. And I'm a professor at Oregon State University. I'm also the co-founder and chief robot officer at Agility Robotics. And this image here shows our digit robots from Agility Robotics in an Amazon warehouse doing this task of moving these plastic bins around. It's kind of falling in the classic 3Ds of robotics, the dull, dirty, and dangerous. There's an awful lot of repetitive stress injuries. It's a little bit dangerous, and it is absolutely dull. So it's a perfect kind of thing for robots, but it's very much a human space and a human environment. It's hard to automate this. A lot of the images and a lot of the stuff I'm going to show in here is from the company, and I'm also going to talk about some of the things from the university and how all of this comes together to really build robots that get out in the world. So I'll start by saying that human-centric robots are going to completely change labor forever. A lot of these tasks that are really just process automated, pick up this thing, put it over here, they're going to be automated, and they should be. And, this gets then into all the conversations about how human time should be very expensive and very valuable, and robot time should be doing all of the things that we'd rather not. Now, I'm calling these human-centric robots, and I'm not calling them humanoid robots, and that's on purpose. A human-centric robot is a machine that is designed to go where people go, exist in human spaces, in environments that are designed around us, like, our businesses, our homes, hallways, stairs, doors, all the things we've designed for ourselves. They're designed to interact with people. They are not necessarily, they don't necessarily need to look like us. They do need to work with us and work in our space. So they are human-centric. Now, as a result of being human-centric, there's a lot of design decisions in the machine that end up looking a little bit humanoid. But humanoid is just a result rather than a goal. Human-centric is the goal. Now, we've built our foundation on hardware that can physically interact in the world the way that, more like the way people do and less like the way robots typically do. And I'll talk a little bit more about that. But I want to point out that some of these modern AI approaches, where AI is a big umbrella describing transformer models and like large language models, but also reinforcement learning, the kinds of things where instead of explicitly writing down an equation or writing down a solution or writing down a model, you're instead writing down kind of what you want and then allowing a system to figure it out through data or through simulation exploration. So that's kind of what I mean when I say AI, and that really makes all of this possible because the generality can really only be done that way. So another point that I'll make, just kind of at the founding, the start of the talk here, is that we're kind of really in a third revolution in robotics. The first one I would identify starting in the 60s with the very first manufacturing robot, the very first robot that was commercially deployed. And these were big robot arms bolted to the floor, pick and place, pick something up in its workspace, set it down, welding, painting, that kind of thing. And that market continues to grow. That's great, but that started a long time ago. Then maybe in the 2000s, we started to see autonomous mobile robots. Now there's things that are rolling around and doing things, but still the whole environment, the whole space is designed for the robots. You have to really modify your environment so that the robots can operate in the warehouse, in the location where these mobile robots operate. But now what's happening is we're able to have robots exist in our space. We're able to have robots that are human-centric. And because so many tasks are designed and built around us, that is a huge opportunity for being multi-purpose. Now that these robots operate in our space and can do the workflows that many people can, and there's so many different tasks and workflows designed around people, Digit can be multi-purpose. That's pretty exciting, and that's part of this whole new era. Now, another thing I'll point out, talking a little bit about the AI question, all of these images are generative. These images are from an AI that created them from a voice prompt where we just said, show us a humanoid robot working in a warehouse, and then we get the image over on the right. That's pretty amazing and still quite new, and something that's going to allow us to ask robots to just do useful things in the space and talk to them in kind of a natural language. Okay. So I'll start briefly, just kind of go through what do I mean when I say human-centric, okay? And like I said, it's for humans, not like humans. This is an analogy to bio-inspired, which maybe you've heard, versus biomimicry. Instead of just trying to copy how a person looks or copy how, the morphology, the shape of it, we're trying to actually understand the basis of why things are the way they are and then implement it that way. So, human-centric starts with the environment, right? Go where we go. Stairs and everything else. Starts with the workflow. What do humans do, and how do you pick something up, and what's the rough scale and weight and size of all the things, and how high can you go and how low can you go, and what's the workspace that we work in? What's the interaction with people, right? We have an opportunity when we end up with a robot that's a little bit humanoid, looks a bit like a person, to use gestures and body language and voice and other things to communicate with the people around it in a relatable and a natural way that does not require people to be trained how to use these machines. Even though they are automation machines, if they're human-centric, they need to come where we are rather than us having to come to where they are. And then finally, I would really point out the design, the industrial design, being able to look at the machine, understand what it does, and be able to snap to judgments that are correct and true, setting clear expectations for what the robot does. That's really important for being human-centric. These things are not peers to us. They are much more like a service animal or something like that in our relationship with them. So we need to be able to set that expectation and set out that kind of relationship. So now, given that you've got one robot capable of multiple tasks, you might say, well, a specialty robot for anything is going to be cheaper and more efficient. And that may be true, actually, but that doesn't mean that it isn't very, very useful to have a multi-purpose robot as well. And we kind of need both of these things. We still have very nice cameras for photography that specialty photographers use when you really need top image quality. But the vast majority of photos taken in the world are on a smartphone. And a smartphone, of course, is multi-purpose. Now, what we're talking about with robots is a machine where it's like the App Store, but for labor, but for doing the physical things in the world. And so having one robot that can do, say, unload a tractor trailer, like in this image, and then, head down those stairs off to go deliver packages out of an autonomous vehicle, and then, be sorting totes on those bins, and then also be interacting with a person. This is in a human space, in a human environment. The robots can come in and just start to do all this stuff. That's when these start to become part of daily life, start to become very, very common, and really, really become useful. So what does it take to get there? Okay, it's an exciting vision. We've wanted this for hundreds of years as humans. First, I would say it starts with the hardware. You can only, the software is limited by the hardware. The hardware is the interface between the AI and the world. An AI is a brain in a box until you've got hardware that can actually physically interact with the world. And it isn't as easy as making something that looks like a person and putting motors on the joints. It is also moving like a person and, getting true dexterity. which is really a holistic combination of the physical hardware and the software that's controlling it. And then another thing that I think a lot of people, especially in academia, may overlook is the commercial engagement is an absolutely necessary piece of this in order to have a use case, an important, valuable application that has metrics and requirements to it. So when we're designing and building a robot like Digit, we can imagine what it will be useful for in the world, right? And we can build a robot that starts to do some of these things. But not until you actually start working with a commercial partner and they have throughput requirements, how many totes per hour, and safety requirements, and they have a specific use case, which is like the number of inches and meters and centimeters and the dimensions of everything. And if you actually show your robot doing something useful, they will pay money for it, right? And that is the best metric for, are you doing something useful? If it's useful, somebody will pay for it. If it provides value, then that's going to produce dollars. And then that's this amazing flywheel that allows us to iterate and improve our hardware and our AI because we're able to actually measure its utility and how effective and good it is. Maybe a better way to describe it rather than commercial engagement would be data. How do you get to 1,000 robots or 10,000 robots deployed in the world? You really have to have a business doing it in order to get the data from those machines, in order to understand the use cases better, and then actually work towards something that's going to be useful in the world. Okay, so we talked about AI and hardware, and I want to break it down a slightly different way here. Like anytime we build a machine, a robot like Digit, there's a hierarchy of the control and the behavior. And, I like in the title of the talk, I call this an embodied artificial intelligence. I'm sure you've heard that before and seen that written before. And like I said, an AI is just a brain in a box until, it can do physical things in the world. And to repeat again, at the basis, we have the physics of the mechanical system. And then above that, we have the controls, which, can be model-based control, can be heuristic-based control, can be reinforcement learned control, doesn't matter. But there's a layer there that is kind of holistically integrated and working with the hardware physics to create the low-level behaviors of what happens when you make contact. And that, combined with some of the planning, we would call the physical intelligence. And really, that's kind of like, what can the robot do? Can it handle stairs? Can it pick up a cup? Can it open a door? What kind of dexterity does it have? Can it go down a hallway? What can a robot do as the physical intelligence? But then on top of that is the semantic intelligence. That's what everybody's getting so excited about right now with large language models and chatbots and so on, is what should the robot do? And honestly, a couple of years ago, if you'd asked me, I would have said, agility is founding everything on the physical intelligence. It's going to take decades of having robots in the physical world to build up our semantic intelligence. But it turns out if you just scrape the internet for all of its information and put it in a giant, large language model, you end up with that human context, kind of the instruction set. So you can say, hey, Digit, clean up this mess. I'll show you a video of that. And then, Digit knows what to do and can, break that down into a set of instructions that then the physical intelligence part of the stack can actually execute on. Okay. So starting at the bottom of the stack, okay, the physics. Physics really matter a lot. And, when we talk about like locomotion, the thing we started with was understanding biomechanics. And I don't care about, where individual muscles are, whether there's a knee joint or where the heel toe, or, the details of the morphology were not the thing that we really looked at. We looked instead at what are the ground reaction forces. When the foot is on the ground, you can measure the forces on the ground. What's the center of mass motion? And then what is the basic behavior divorced from the implementation details of an animal? Because we're building machines. We don't have muscle and bone. We have aluminum and electric motors and computers. So, first understand biomechanics. And this applies to manipulation as well, and studying how people grasp things. And I might make this point a few times, but the morphology or the shape of the machine is really just the tip of the iceberg. It's like one symptom, one small piece, and not even necessarily the most important piece. So these robots on the far left, the early robots, the monopods there on the stand, those were the early science machines that are trying to reproduce this spring mass behavior, but in a machine. And, we looked at just the math model. We ignored anything about trying to reproduce the morphology or the shape or the joint structure of an animal or a person. And that's the foundation then, when we showed that operating, that allowed us to continue to iterate all the way on up towards the digit we have today, which is working in warehouses, capturing some of the same physics, but now it's a fully 30-degree of freedom robot that's really moving around in the world. So here's a nice video, hopefully you can all see this, of Atreus. And Atreus, like I said, was a science project meant to reproduce the dynamics that we observed from animals. This is several years old. So the graph on the bottom is a collaboration with Monica Daly from the Royal Veterinary College, where we measured the ground reaction forces of all of these different ground-running birds of all kinds of different scales. So we wanted to make sure we aren't, getting some nuance of a particular specific animal or specific bird. We wanted to understand what is true across all animals, all bipedal locomotion, and then make sure we captured that into a machine. And this hypothesis is that this math model that did represent how animals really describes this special corner of dynamics, this self-stable behavior of locomotion. And Atreus ultimately was the very first machine ever to reproduce the dynamics of a human walking gait. And a little bit into this video, you can see that. Here you can probably see that it's walking and running, and you can see, of course, the morphology, the shape of it is this 4-bar linkage, nothing like a person. But here, the walking dynamics, look at the ground reaction forces. On the left is the robot. Let me pause that there. On the left is the robot, and on the right was the person. And you can see they're awfully close. So this is one symptom, one thing that shows us that we're capturing the right physics of locomotion. The other is, hey, it's walking and running outdoors over all kinds of terrain. It's totally blind. There's no planning. There's no camera. There's no perception. Yet we can go over all of this terrain. So, there is this special corner, this self-stability that we're getting by capturing the right physics of locomotion. Okay, so these are the foundations. And I want to point out, the hardware, the physical, mechanical pieces of the robot, they have to be special. You can't just put the motors on the joints. You see how this robot is moving organically. It's not moving robotically. This is not a position control trajectory. It is not a position trajectory. It is much more about forces that we're applying on the world. And so we need special actuators that are actually controlling the force and able to control the force at a high rate. It's about impedance and compliance and flexibility when it makes unexpected contact with the world. They have to move organically, not robotically. Only if you have your hardware foundation and your physics integrated in that way can you hope to then learn how to do natural walking and running gaits. And again, this applies to locomotion or manipulation. I don't think there are that many differences between locomotion and manipulation. I think of it all as one kind of loco manipulation challenge. All right. So, the hardware physics, when you're designing a robot, that's not something that you can learn. You can't have a computer just use a machine learning algorithm and spit out a design yet, maybe in 20 years or 100 years, or I don't know, sometime in the future. But today that's engineered. That's engineers who understand the physics and understand what they're trying to achieve and can work with various vendors and manufacturing processes to create the machine that you want. But then, kind of the next layer up, the controls, that can be heuristics and model predictive control and things where engineers are writing down the equation, the solution. And it can include learned approaches, reinforcement learning and other approaches. All of those things are really applicable in different ways for controls. But one thing that's true is that all of this must be explored in simulation. So the physical intelligence of this is not something that can be data-driven. You'll see a lot of people talk about using teleoperation to control these things, and you learn from teleop in order to have a machine do useful things in the world. I don't believe that fundamentally can work. I feel that you can sometimes, and we have seen examples and demonstrations of people, after teleoperating a humanoid robot, then the robot can reproduce that task, but it's extremely brittle. It is very, very brittle, and only in the very specific scenario within the constraints that the data was taken can it operate. It isn't generalizable. It isn't stable the way that we showed that locomotion over all kinds of terrains. And that's because you can't possibly get enough data that is specific to the dynamics of this piece of hardware that you've designed to cover all of the potential applications and use cases. So the type of data is really not that relevant. Maybe you can get a position trajectory, but you have no idea what the forces are or what the input torque commands to the motors or any of those things. And more importantly, you can't get anywhere near the volume of data. In order to train some sort of a diffusion model or a large language model or something like that, the amount of data that it requires is vast, which is why, scraping the entire internet works for some really interesting chatbots. But connecting enough data of controlling a robot, I don't quite know how to do that unless you already have a controller for the machine. Teleoperation isn't it. So, the way to do that is you got to simulate it. You got to use something like reinforcement learning approaches that can actually explore all of the corners of the dynamics and all the possible capabilities of what the machine can do, the simulated machine, but a high fidelity simulation. And then find solutions and be able to explore and discover those solutions, discover that weird nonlinear manifold that is your policy for controlling some behavior on the robot, like walking or grasping or something like that. So the important piece to take from this is that for the physical intelligence, it has to be simulation driven. It cannot be data driven. You're not going to learn a policy from data. You're going to have to explore the policy in simulation for the physical intelligence side of it. And here's, an example of us doing that. These are just an animation of less than 1% of all the different, tests that were done on Digit to try and learn kind of a walking gait as we do a learned policy for this thing. And none of these in this particular image have fallen, so we've already pruned the 99% of solutions that include falling. And now we have all the different solutions that are walking. Some of them are walking at a velocity like we want them to, some of them aren't. And so, of course, there's a cost function that we're measuring and figuring out which of these is the one to kind of prune and which of the ones we want to bring forward. And then we get to, the sim to real transfer video. Here it is in simulation. And here it is on the robot doing the exact same behavior. Sim to, if you've got the hardware, you understand the physics of your hardware, and it's clean enough that you can simulate it. All right. So let's see. Same video as before, but the point I want to make is that this success of going from simulation to real depends on having this robust physical intelligence, because you can get to really brittle solutions in a simulation. And so you kind of, in your simulation, you have to have inaccuracies, you have to have noise, you have to include all of the kind of stochasticity that you're likely to see in the real world if you want the robot to be robust to that in the real world as well. And I guess a story to tell is when we first started doing we took Cassie, our bipedal robot, and had it run a 5K on a learned policy. When we first tried to do that, it worked great on our treadmill in the lab. When we took it outside, the very slight sideways slant, because the road wasn't quite flat, it had a slight crown to the road so that water can drain off, like less than 1 degree, was enough to totally destabilize the robot. It would just fall off to the side, one or the other side. We had to go back and spend another few months training with, on all kinds of different surfaces that weren't flat in order to get this thing to actually be robust outside. And here it is. So this is Cassie now running this 100-meter dash. This is all, using reinforcement learning to create this behavior. And, first off, of course, the robot has to be capable of this with impacting that ground over and over and having that compliant and impedant control. But then exploring this behavior in a learning environment and simulation is the only way to get such a beautifully natural gait. This is not constrained by some oversimplified model that we have. This is not a linear inverted pendulum model. This is not zero moment point. This is bouncing along. This is very much spring mass locomotion, but with crazy inertial distribution in the legs that make it a real bear to try to control using any other method. So I'm very excited about these kinds of approaches. All right. So here too, and this is not a brand new of it. You can see that Cassie steps right on the edge there of the stair and then is able to recover. Here it is in slow-mo. You can see its toe is caught right on the very front edge of the stair, and yet it steps backward and forward. And that's because this is the stair climbing policy. It saw tens of thousands of stairs, in simulation. So even with no cameras, it's able to identify, it's able to create a gate where it's stepping high and it will be able to recover even if it stands on something that it doesn't expect. Step up, step down, it doesn't need to know. Now, if you add some perception to that, stronger behavior. Let me move this. So this is Cassie. It does have a camera on the front of it. It is creating a depth map of its environment. So it's able to interpret something. That depth map, of course, is kind of noisy. So it is important to have the robustness that you saw before of the locomotion being completely blind. But you can also see here that it's taking sort of small steps on the flat ground, and it does see when there's something coming up and steps up pretty high. Now, sometimes it misses the step. It steps high before the step it comes in, or it steps off the edge of something in a way that it didn't expect. And just like a person, it's something that's maybe a surprise, but the robot can handle it. So that's kind of the benefit of having this kind of hierarchy of layers of a robust gate that can work while blind, then adding some information with some perception on board. Okay, so now here we are with Digit, in our basic simulation, and this is just the physical intelligence. So this is all of the, can the robot pick something up? Can the robot walk around? And then human engineers lay out the workflow for it. Human engineers tell it which tote to pick up and where the totes are. Human engineers have created the CAD model to show the robot exactly what its environment looks like. And then there's QR codes. You can see them down in like the lower left of the video that help the robot's perception system to localize itself within the frame. In fact, on the right side, you see the little squares that say 7, 8, 9. Those are the QR codes. That's the thing the robot can see. Everything else is something that humans drew the CAD model that should correspond exactly with what is in the real world. And then the robot is basically just operating within its own internal CAD model, which happens to correspond with the real world. So there's really not a lot of, sophisticated perception going on here. There's not a lot of, basic autonomy and basic planning is happening, but not a lot of intelligence or major decision-making is going on. This is just the physical intelligence. And you can still do really useful stuff just with that. And we are. That's part of the foundation of our initial deployments. Okay. However, if you actually want to do useful things more broadly, in a more versatile way in the world, you need this semantic intelligence. You need kind of the human context, so the robot will actually be able to decide what to do in an environment that is uncertain and has a lot of human artifacts. I mean, how would you learn what a cup is or a chair from simulation? You simply can't. You have to pull that in as a data-driven approach. And that's what generative AI is pulling in data in order to build a model that the robot can then learn from. Of course, it's a brain in a box without the physical intelligence, but it really unlocks the versatility and the variety of things that the robot can do. And that's going to be completely necessary when a robot is operating in human spaces. So in our initial demos, we've shown what we call, or this is a term of the art, not what we call, but what is called a chain of thought LLM prompting approach, which kind of gives the whole continuous ongoing set of things that the robot is going to do. And that allows it, if something about the environment changes, it's not a plan, the robot can change its plan on the fly, can basically change its mind, given new information. And I'll show a quick video here. Okay, so the prompt at the beginning of this, you can see there's some bubble wrap there. There's a cardboard box. There's a plastic jug. And there's 3 bins labeled paper, plastic, trash, And the command to Digit was verbal and said, Digit, clean up this mess. And so it's entirely up to the LLM, which is, data pulled off the internet, to have the human context to understand what is mess and what is cleanup and, interpret what does one do to clean something up. And in fact, you saw here at the beginning, the bubble wrap that Digit picked up off the ground, it chose to put in the trash bin and not the plastic bin, because Digit knows from the context of the internet, I guess, that bubble wrap is not recyclable and should not go in the plastic recycles. It should go in the trash. That's not something we programmed. That's something that now an LLM just enables us to do when we connect it up to the physical intelligence of, and it can just give direction. So the LLM here is directly programming the API of the robot. In other words, Digit can do these things physically. We could have had an engineer write out the list of tasks that the robot should do and in what order. But instead, we just told the LLM, what is your interface? What is the programming language for the actions that Digit can take? And translate then the command from the person into the programming language for Digit. And that's what it was able to do. And this only took about 2 weeks from start to finish to implement that, which really illustrates the power of these new tools. Pretty exciting. And by the way, these tools are like a commodity now. There's any number of different companies that are creating these highly intelligent chatbots that you can interface with, and it's very inexpensive to use. So something that was next to impossible 10 years ago is practically free now, which is just amazing. We're just going to have to watch all the applications that they use. So here's another recent one. The command here is kind of a joke from, there's a video a while back with the CEO of NVIDIA, Jensen Huang, saying, hey, what's cooking? And he went and pulled a couple of GPUs out of his oven to show what NVIDIA is up to. And we were there visiting NVIDIA recently, and we asked Digit, hey, Digit, what's cooking? And you can kind of see here in this video what Digit's thinking, saying, I should find out what commands I can use. I should get a sense of my surroundings. I will acknowledge my co-host and wave, and then say, hey, there's some GPUs that are cooking. Now I'll use my wave command, and I will go to the oven. You can see the train of thought. You can see the different tasks that are coming forward from one to the next. And then Digit's picking it up and going to bring it out. So we did this for Jensen Huang, and it was great. Here we go. Here it is, by the way, in simulation. This is using Isaac Sim on the left, and then the Digit robot on the right. So it's good to have a way to simulate things and have some kind of a digital twin. So I know you all know this because, we're a lot of roboticists in the room, but AI is really a big deal right now. It's going to change the world. It already is, but it's completely enabled by the hardware. You have to have the physical intelligence as a foundation to be able to do the physical things in the world. Having an LLM at the top is great for this cognition. That is sort of interchangeable with, in our case, applications engineers who set up a workflow. Now you can have an LLM kind of lay out the workflow and tell the robot what to do. But the planning, the controls, the physics, that's more like reinforcement learning, broader machine learning approaches, and a bunch of novel hardware design. I mean, we're really working on actuator designs to make them transparent and be able to impact the ground and not be so rigid like a robot, which is a hard thing to do. And of course, manipulation is one of the grand challenges in robotics. And having manipulators that are going to be anywhere near as dexterous as a human hand, same problem. Hardware enabling AI. I think a lot more is possible now than it was 10 years ago, but we've got a lot of work to do. And boy, what an exciting time to be working on this stuff. So I kind of see, as I'm getting close to the end of my talk here, I'll have a few minutes for questions at the end. We're kind of on these eras of progress with these human-centric robots. Our conviction is that you can't just start by saying, we're going to build a general purpose robot and embodied artificial intelligence that will help us around the house. That's certainly the goal we all want to get to. But our conviction is that the fastest path to do that is to start first with one of these multi-purpose robots where your vision is multi-purpose, doing one thing, even one thing reasonably well. And I call that era one. Just one or a few of these multi-purpose robots, just doing a single job pretty well. Then era two is growing out to hundreds and thousands of these robots that can do something. And again, that requires commercial engagement, that requires the metrics of showing that you are meeting requirements for a company and solving a problem for somebody that they're willing to pay for. That is the only way you get to era two, proof of scale. Then era three is when you start to say, do your second task really well, your third task really well, and you have the single robot that does one primary job and then starts to be able to do 2, 3, 4, and you're starting to get into that app store, but for labor. And that really becomes we start to really enter this revolution in robotics that are in human spaces and human environments. While we're doing that, we're learning the safety, we're learning the reliability, we're learning the decosting. And we then can get to era four, where you end up with businesses, they can just buy a robot and then just teach the robot how to do what it does. And then it's working in grocery stores and hospitals and other places. And eventually, we're going to get to the point where they are so safe, so easy to use, and so inexpensive. We get to have robots in our houses and have them help us around the house with chores and be a telepresence machine and so on. But the path to get there is to start with the robots that do the useful things first. So this embodied artificial intelligence, it enables generality. It's going to bring robots into our everyday life. And I couldn't be more excited about it. So I will stop there, and I would love to have a few questions from people. I'm going to stop sharing my screen here so that I can see you, and then we can talk for a little bit.
Thank you so much, Jonathan, for a really inspiring and exciting talk. Thank you so much. So yeah, I have a few questions, but maybe just to start us off, actually, for me, it has an interesting question of saying legs were useless 25 years ago. What were the tipping points or the kind of the changes, hardware or software related, that have taken you to where you are now?
So legs were used 25 years ago, but think about this comparison, right? I talked about how the morphology is just the tip of the iceberg. And, we did have robots that could pick up one foot and place one foot in front of the other. But that's different from having robots that can truly coexist with people and go where people go. So if you take a humanoid that we're all familiar with, many that have been built, and you imagine lifting it up off the ground by maybe half a meter off the ground, and then drop it. And what happens? And then I would say that no matter what software you've written, when it hits the ground, it's going to hit like a ton of bricks. It is going to break things in the leg. It is going to land in a very rigid robotic way and not at all absorb that the way that a person would. Now, there's just a few people and a few groups, Boston Dynamics and Mark Rayburn early on had these highly dynamic robots, but most machines are not like that.
Yeah.
And so we were very much kind of in that same camp of understanding animals and biomechanics, and a lot more dynamic, the way that you saw some of the Boston Dynamics machines. And, Atreus was dramatically different from almost all other legged robots, just to focus on those physics and those dynamics. I would say that now I'm watching companies like Tesla bark up the same wrong path, where they have, hardware that really can't handle impacts. And so they're showing walking gaits that look exactly like the last 30 years of humanoid walking. And they're going to figure it out because the amount of dollars going into this iteration and the number of engineers hitting their head against this problem, they're going to figure it out. And so I think that's one of the biggest differences, is just early on, it was a very few people with a specific insight. And now it's such a community and so many resources and so many people working on it. We're going to figure it out. It's very complicated. There's a lot to it. That's why.
I'm wondering, in terms of manipulation, how far do you made such huge advances in leg locomotion. In terms of manipulation, how far do you think we are away from having a similar dexterity that's seen in humans to where you are with locomotion?
I think we're closer than it looks, because I think that once we get, again, hardware that's good, and 99% of manipulators are not good, in my opinion, in terms of real dynamic compliant dexterity in the world. Same kind of thing. If you were to have the robot hands, and say the robot falls over and your hands are going to hit the ground first, they're going to shatter, So how do you have something that's really compliant? there's a few examples of people who are thinking about that, but they're so hard to control, which is one of the reasons why even throughout history, like my favorite hand is Ken Salisbury's dexterous manipulator from, like, I don't know, it might have been the 80s. It was this cable drive three-fingered manipulator, very dexterous.
Yeah.
But you know, how to control that is so hard. AI is going to let us control those really weird things now. So people are going to, this is another one of those things. People are going to be working on it. We're going to be figuring it out pretty quickly. It's a priority for agility robotics to figure out manipulation. So right now we think about manipulation as like digits, a whole body loco manipulator. And that's why we're starting with boxes, because you can do the bimanual manipulation. And you can think about that as like a pincher grasp, just a really big pincher grasp, right? Pretty basic manipulation of large objects where we are using the environmental constraints, you know, to slide the thing out to run into stuff. And that's why you need the compliant interaction. We're going to need to be able to pick up individual objects too. So we're going to need to figure that out. It's coming though. Did you see Atlas with the 3 fingers picking up the big, you know, shock suspension thing and put that in? Fantastic. Now, Atlas is not a product, can never be a product, but it's still a technical demonstration of that I think is significantly better than any of the demos you've seen from Figure or 1X or any of the others, which are very, very much a position, trajectory, brittle sort of video demo. Very different from doing something physically real in the world.
I'm interested in what you think about the whole code. So you're kind of having a very hardware-driven, hardware, we have the physical capabilities, and then we add on top of it the semantic intelligence, decision-making. What do you think, at least kind of there's quite a lot of talk about co-design and kind of the soft robotics world, and also kind of the Evo, Devo. Where's the role of developmental robotics in what you're doing? Does that come into the sim to real, that it's the learning potential on some bodies are more than others, and that can help with the sim to real transfer? I wonder if you have any thoughts.
Well, for sim to real transfer in particular, what we found is the secret is having the system be robust to all the kinds of discrepancies and errors that you're likely to see. So like even early on with Atreus, we had a simulation. It wasn't particularly great. Like simulations are pretty bad with, you know, rigid body contact or soft compliant. Anytime there's contact, making and breaking contact. Sometimes they're sticky. Sometimes they penetrate the surface and then come back and then kind of slide along it. You never know. And certainly that happened in our controller as well, or in our simulation as well. But the trick is that because Atreus is this big spring mass model, things that happen at the foot, even if they're wildly off by like a factor of 5 from what's real, it doesn't really affect the overall dynamics of the system very much. The system is just very insensitive to those kinds of contact errors. So then in the real world, you know, we assume that there's a rigid ground, but it turns out we're running on really soft, mushy grass that's rained the previous day, or gravel or mud. Same kind of uncertainty, right? And still, the robot's very insensitive to those kinds of discrepancies. It doesn't really care what it's running on. That's why we got such great sim to real transfer. So I think that's the secret, more than most things, is to have a system that's very robust to the type of disturbances you're likely to see.
Thank you. Nice. So maybe we could just finish with a couple of questions from the chat. One is about, so you showed LLMs in terms of the kind of the decision making and having this kind of contextual awareness. Is there potential, or how could LLMs be used to improve terrain sensing or gait adaptation?
I think that identifying what's in a scene and kind of knowing something about what you're seeing and updating that is going to be one of the primary uses. I don't think LLMs are good for planning. I don't think LLMs are, like, they hallucinate. They tell you things that are wrong. They don't necessarily know when they've reached a goal. It can just sort of, you know, feed back patterns of what it has seen before. So that's really great. That's really useful. But I think that it's part of a hierarchy. You know, I think maybe at the highest level, you've got the LLM, which is interpreting the world and being able to interpret any language or other things to feed instructions to the next layer. But then I think you're going to need something else that's a planner. Now, maybe you can do something diffusion related and data driven that is a planner. I don't exactly know. So we've got some work to do.
Thank you. Thank you so much, Jonathan. Now we go to the next panel discussion. I don't know if you've got time to join for that, or if you have to head on. But we have some additional panelists to join us just to wrap up today and today's discussion. So once again, thank you very much, Jonathan, for joining, and such an inspirational talk.